In this video, we're going to discuss how to find power series representations of functions using basic algebra. The starting point for many power series representations is the function 1 over 1 minus x, which, as long as the absolute value of x is less than 1, is equal to the standard geometric series, the sum from n equals 0 to infinity of x to the n, which is 1 plus x squared plus x cubed, and so forth. We can use this power series representation for 1 over 1 minus x, along with some basic algebraic rules that we can use with power series in order to find the power series representations of even more functions. The basic algebraic rules for power series that we'll be using are the following. Suppose we have two functions, f of x and g of x, and we have power series representations for each of them. In particular, let's say that f of x is given by the power series n equals 0 to infinity of a sub n x to the n, and g of x is represented by the power series n equals 0 to infinity of b sub n x to the n. We can use these two power series representations to find power series representations for f of x plus g of x, f of x minus g of x, c times f of x, where c is any non-zero constant, and x to the k times f of x. We can do this in the most natural way possible. To find the power series representation for f of x plus or minus g of x, we simply add or subtract the coefficients in our two power series for f and g individually. And so the new coefficient of x to the n would be a sub n plus or minus b sub n, respectively. If we multiply our function by a constant c, we can simply multiply each coefficient in our power series representation by that same constant c. And if we multiply our function by a power of x, say x to the k, this simply increases the exponent of x in each term of our power series by k. Notice that in all of these cases, the interval of convergence is unchanged. So if f and g are both defined on a particular interval, so will f plus or minus g, c times f, and x to the k times f. In this example, we want to represent the function f of x equals x squared over 4 minus x squared as a power series, and then find its interval of convergence. Our goal is to rewrite the function formula for f of x, the x squared over 4 minus x squared, in such a way that we can utilize the power series representation for 1 over 1 minus x. This means we need to get this down to some variation of 1 over 1 minus some expression. In order to do this, we can manipulate this function in a couple different ways. First, to get a 1 in the numerator, we could rewrite this as x squared times 1 over 4 minus x squared. And this gives us part of what we need. We have the 1 now in the numerator, and we're multiplying by a power of x, x squared, and one of the properties we just discussed tells us how we can deal with that once we have a power series representation for the remaining part of our function. So now we look at 1 over 4 minus x squared. In order to get this into the geometric form, we do need this constant in the numerator to be a 1. And so what we actually need to do here is factor a 4 out of the denominator. And so we're going to have x squared times 1 over 4, and then the remaining part, once we factor out 4, is going to be 1 minus x squared over 4. Of course, we can now bring the 4 out in front, and so we're going to have 1/4 x squared times the function 1 over 1 minus x squared over 4. And now we have exactly what we want. We have a function base here of the form 1 over 1 minus something, and that something here is x squared over 4. And we're multiplying it by a constant 1/4 and a power of x, x squared. And our algebraic properties tell us how we can adjust the series to account for those two values. So here, we're going to replace our base function with the geometric series that we would obtain. So that would be n equals 0 to infinity of x squared over 4 to the n power. And now we just do some algebra with this. We, of course, have 1/4 x squared. Our series term, when we expand this out, we're going to see that we get a 1/4 to the n multiplied by x to the 2n. And so we have 1/4 x squared, sum n equals 0 to infinity of 1/4 to the n x to the 2n. Using the property with constant multiples, we can multiply each term by 1/4. We can bring that 1/4 inside our summation. And we're going to get the sum from n equal to 0 to infinity of now 1/4 to the n plus 1 power. We had 1/4 to the n. We add another, multiply by another factor of 1/4, and that increases the exponent by 1. Now we have x to the 2 out here, x squared, and we can bring that inside as well using an algebraic property, and that would add to our exponent of x. So now we have x to the 2n plus 2. And so this is our power series representation for our function x squared over 4 minus x squared. We have the series from n equals 0 to infinity of 1/4 to the n plus 1 times x to the 2n plus 2. In order to find the interval of convergence, we simply need to use the fact that this was derived from a geometric series and determine for which values of x the expression x squared over 4, the expression we substituted into our geometric series, will have an absolute value less than 1. So, to find when this converges, we need to solve the inequality of the absolute value of x squared over 4 less than 1. Now here, notice that x squared over 4 is always a positive number, and so we can simply drop the absolute values here, since we're taking the absolute value of a positive number. We can then multiply both sides by 4 to get x squared less than 4. And x squared will be less than 4 whenever x is between -2 and +2. And so this will be our interval of convergence for this power series. And so we have the open interval from -2 to 2 with neither of the endpoints included. If you'd like to try a similar problem, pause the video and represent f of x equals 3x over 1 plus x squared as a power series and find the interval of convergence for that power series. Resume the video and see the full solution in a few seconds. We start by rewriting this function as 3x times 1 over 1 minus quantity negative x squared. 1 over 1 minus negative x squared can then be rewritten as a series using the geometric series sum formula, and so we have 3x times the sum from n equals 0 to infinity of negative x squared quantity to the nth power. We can simplify the term of this series to obtain 3x times the sum from n equals 0 to infinity of -1 to the n times x to the 2n. And then we can bring the 3x inside the summation by multiplying by a constant of 3, and multiplying by x here means adding 1 to the exponent of the x to the 2n term. And this gives us a final power series representation of the series n equals 0 to infinity of 3 times -1 to the n times x to the 2n plus 1. Since we're using a geometric series argument here, this series will converge when negative x squared will be less than 1 in absolute value. This amounts to saying when x squared is less than 1, which is between -1 and 1, and so our interval of convergence is the open interval from -1 to 1. In this example, we want to represent the function f of x equals 1 divided by x minus 1 times x minus 3 as a power series. The function's form here is quite different than in previous examples. In particular here, the denominator is much more complicated as a product of two expressions, x minus 1 and x minus 3. We ultimately want to make the denominator have the form 1 minus something, but this is really not feasible the way the function is currently written. Fortunately, since we have a rational function here, we can rewrite it using partial fractions in a way that will let us have rational functions with simpler denominators that we can manipulate in the way that we want. And so here, we'll leave the details to the viewer to confirm this partial fraction decomposition. But using the standard partial fractions approach, 1 over x minus 1 times x minus 3 is seen to be equal to negative 1/2 over x minus 1 plus 1/2 over x minus 3. And so we've now written our function as the sum of two functions with simpler denominators. We're now going to focus on each of these separately and rewrite them in the appropriate form so that we can apply the geometric series representation to them. So in order to write these in the appropriate form, the first thing that we notice is that we need the denominators to be subtracting x as opposed to subtracting constants from x. In this case, one approach to get the denominator into the form that we want is to factor a negative out of each of the denominators. And so here, when we do that, in the first function, when we factor out the negative, the denominator becomes 1 minus x. And we can move that negative to the numerator and combine it with the negative 1/2 to become a positive 1/2. And so our first function is equal to 1/2 over 1 minus x. We can do the same thing in the second term. We can factor out a negative from the denominator to get a 3 minus x there. And this then can become a negative 1/2. So here we're going to subtract 1/2 over 3 minus x. We'll now deal with the constants in the numerator of each of our expressions, as well as the 3 in the denominator for our second one. For our first expression, we can bring out the 1/2 and rewrite this as 1/2 times 1 over 1 minus x. And this is a perfect form because 1 over 1 minus x is exactly the sum of the geometric series with term x to the n. And so we'll be able to easily utilize the geometric sum formula for that term. For our second expression, we can certainly bring out the 1/2, and then we're also going to factor a 3 out of the denominator. And so when I have a 1/2 and another factor of 3 in the denominator, that gives me a constant of 1/6. Our numerator will be 1, since we factored out or brought out the 1/2. And if we factor a 3 from the denominator, we're left with 1 minus x over 3 in that denominator. So now we are set up to write these all as series. So we have 1/2 times the series from n equals 0 to infinity of x to the n. That is the straightforward geometric series, minus 1/6 times the series from n equals 0 to infinity of x over 3 to the n. Now that we have each of our functions written as series, we can combine our series by bringing the constants inside and subtracting our series using the algebraic rules that we've discussed. So we can deal with our constants by bringing them inside each of our series. So we have the series from n equals 0 to infinity of 1/2 times x to the n minus the series from n equal to 0 to infinity of 1/6 times 1/3 to the n times x to the n. So here we're also breaking up the x over 3 to the n as the constant 1/3 to the n times the variable x to the n. And now we have the difference of two series. And the coefficients here for our series are 1/2 and 1/6 times 1/3 to the n. And so when we combine this into a single series, we can simply subtract our coefficients in the appropriate manner. In this case, that would be 1/2 times 1/6 times 1/3 to the n, all multiplied by x to the n. And so this coefficient here in parentheses is an minus bn, where an and bn are the coefficients of the two series that we are subtracting. And so here we have a single series representation. Our coefficient is the number 1/2 minus 1/6 times 1/3 to the n, and multiply that coefficient by x to the n. And this is our power series representation for the function that we started with f of x. If you'd like to try a similar example, pause the video and represent the function f of x equals 1 over 1 minus x times x minus 2 as a power series. Resume the video, and in a few seconds, you'll see the full solution. The first step is to rewrite our function using partial fractions. So here 1 over 1 minus x times 2 minus x can be rewritten as negative 1 over 1 minus x minus 1 over x minus 2. We can then, in the second term, factor out a negative from the denominator, which makes our second term positive 1 over 2 minus x. We can then rewrite each of our terms dealing with our constants. So our first term will be negative 1 times 1 over 1 minus x by bringing out the negative 1 from the numerator. And our second term can be expressed as 1/2 times 1 over 1 minus x squared by factoring out a 2 from the denominator. We can then replace 1 over 1 minus x with the series from n equals 0 to infinity of x to the n, the standard geometric series, and the 1 over 1 minus x over 2 with the series n equals 0 to infinity of x over 2 quantity to the nth power. We can bring our constants of negative 1 and positive 1/2 into the summation. In the second sum, we're going to combine that with the 1/2 to the n that's already there to result in 1/2 to the n plus 1 multiplied by x to the n. And then we combine our series together. We add our two series here by adding the coefficients. So we end up with the power series representation from n equals 0 to infinity of negative 1 plus 1/2 to the n plus 1 times x to the n.